We present FastNeRF, a Neural Radiance Fields method capable of rendering high-fidelity content orders of magnitude faster than previous approaches.
Neural Radiance Fields, or NeRF for short, is a recent method that allows for capturing a high-quality representation of a 3D scene within the weights of a neural network. This network maps position and direction to color and density, which can be integrated using traditional volume rendering. The one downside of NeRF is that it takes dozens of seconds to render a single image. This means that in order to run NeRF at interactive frame rates, resolution needs to be drastically reduced.
To overcome this limitation, we introduced FastNeRF, a method that accelerates NeRF's test time speed by 3000 times while largely retaining visual quality. The reason for NeRF's slow speed is that its MLP needs to be queried more than 100 times for every generated image pixel. For large images, this requires millions of forward passes through the network. Instead, we propose to replace the neural network with a cache that can be efficiently queried at test time. To generate the cache, we sample the input space of the network in a way that covers the scene we are modeling. We then compute the network outputs for those samples and save the input-output pairs in the cache. Note that the cache needs to be generated only once and after the training is complete. To apply the caching scheme to NeRF, we need to create a single cache for its 5-dimensional input space. Such a cache would scale proportionally to the number of bins per dimension to the 5th power. Even for moderate cache resolutions, this means that the cache size quickly becomes prohibitive.
To make caching feasible, we propose a new graphics-inspired neural network architecture, which we call FastNeRF. FastNeRF factorizes the problem into two subnetworks. One that is dependent only on sample position, and one that depends only on the ray direction. The position-dependent network outputs a deep radiance map. The view-dependent network outputs weights that scale the components of the deep radiance map to obtain a final RGB value at each sample position as seen from the specified direction. FastNeRF's factorized architecture allows for separately caching the position and direction-dependent networks. This makes caching feasible as it avoids the memory explosion of a 5-dimensional cache. Note that since FastNeRF uses the same set of inputs and outputs as NeRF, it can be used as a drop-in replacement for many methods that already use NeRF.
Here is a visualization of the deep radiance map components produced by the position-dependent network. Here we show a qualitative comparison to NeRF. Here, we demonstrate how cache size influences render quality. Caching a trained model allows our method to easily trade memory for quality as required, much like LODs do in computer graphics. We observe that the direction-dependent network can sometimes overfit to the data, which results in flickering as the camera position changes. To counteract this, we propose to simply use a similar cache size for the direction-dependent component weights. Please see the supplementary materials for further details. Our method can be applied to a variety of scenarios enabled by extensions to NeRF. Here, we show an example application to telepresence where we animate a person's face using FastNeRF combined with a deformation field network. As FastNeRF takes only a few milliseconds to render these images, the deformation network becomes the main bottleneck. This lets us achieve 30 frames per second in practice.
Due to its simplicity and generality, we hope that FastNeRF will enable the use of neural rendering on consumer devices, including for virtual and augmented reality applications. For further details, please see our paper. Thank you.